Let's not. Okay, this section is on logarithms, and I realize you saw logarithms in 1050. Logarithms for many people are kind of difficult. So going over them again and hitting the basics, and there are some more advanced things that we're going to talk about in this section, and we're going to add to those in the coming sections in chapter 6. So logarithms and exponential are really important types of functions. It's very important that you understand those, and it's also important that you understand this. Exponentials are pretty easy, okay? It's not very hard to wrap your mind around how those work. Logarithms are a little bit more difficult because they are the inverse of exponentials. The same way division is harder than multiplication, logarithms for most people are more difficult than exponentials. Okay? So let's take a look at the starter question here. It says, what is the two-step process for finding the inverse of a function? What do we do first, Amelia? First thing we do is we switch x and y. And what's the second step? Solve for y. Solve for y. Now, I realize some of you would know how to finish this one off, but the second part of the starter question is use the two-step process to find the inverse of exponential base 2. Remember, this is what we call it, exponential base 2. So I'm going to switch the x and y, and I get this. The problem here is I need to get that y down where I can work with it. I need to solve this. And the only tool that will do that is a logarithm, and that's what this section is about, okay? So the first thing we're going to do is, again, we're just going to remind ourselves that if you've got an expression that looks like any one of these, they're not that bad, okay? If I have 2 to the third, everybody knows that's 8. If I have 3 squared, we know that's 9. We know we're using the base, 3, twice because the exponent is 2. If I have a 4 to the negative 2, not very pleasant. We know the negative means reciprocal, so this is 1 over 4 squared. So the answer to this one would be 1/16. This one also, not very pleasant, but we know if we're raising something to a fractional exponent, the numerator is the exponent, the denominator is the root. So this is the square root, so the answer here is 4. Okay? Now, the structure of these problems is very similar. They've got bases, they've got exponents, but it's a little bit different. What's missing is not the number over here, not the answer to the exponential. What's missing is the exponent. Now, a couple of these are pretty easy. If I look at this one right here, it says 3 to the question mark equals 27. 3 to what power equals 27? 3. So the answer there would be 3. If I do this one, this is a little bit more difficult because this isn't a power that you would have memorized. 7 to the x equals 343. We're missing that exponent. That is a much more difficult problem than what we were asked on this line right here. Now, if you grab your calculator and just start doing 7 to the first, 7 to the second, 7 to the third, 7 to the fourth, maybe you'll get lucky and at least come in within a ballpark of it. It happens to be, anybody, I saw some calculators get pulled out there, happens to be 7 to the third. 7 to the third, okay? So that x in this case would have to be 3. 7 to the third equals 343. This one right here, this one's not very hard because we just answered it right here. It's the same expression, it's just a different part of that expression that's missing. So the answer here would be 1/2. Now this one right here is a much more difficult problem. Because unlike this, even with the use of a calculator, you can sit there and go 4 to the first, that's 4. 4 to the second, that's 16. 4 to the third is 64. So you can know that it's somewhere in between 2 and 3, probably closer to 2. But without a logarithm, you can't know exactly what the answer is here. Okay? So this problem right here is perfect for logarithms. Okay? So let's remind us of what a logarithm is. Okay? This is an exponential equation. This is exponential base b. And there are 3 parts to an exponential equation. There's the base, there's the exponent, and for lack of a better word, there's the number that it equals. Okay? So once I take the base, raise it to that power, I get a number out of that. Or at the very least, some expression. Logarithms are just another way to write an exponential expression. In fact, down here in this box right here, that's the first thing that will help you understand what logarithms are. They're just a different way to express something that we're more familiar with, an exponential expression. So all we have to do is figure out where these three things go. This is called exponential base b. This is called log base b. Okay? We write the base down here. Okay? And the second thing is the answer to a logarithm is an exponent. So if I'm going to represent these three things over in this logarithmic expression right here, logs have base just like exponentials have bases, so I'm going to put the base right here. It's usually written smaller and a little subscript. And the answer to the logarithm, the thing that goes over here, is the exponent. So it's an x. So the only other choice I have here is that's got to be an n. Okay? Any questions there? So this is log base b. Sorry, this is exponential base b. This is log base b. They're just different ways of writing the same type of thing. Okay? Again, here are the two things that you want to remember. Logarithms are just a different way to write exponential expressions. And the answer to a logarithm is an exponent. Makia.
Can you solve a logarithm without a calculator?
It depends on what the logarithm is. Okay? Most of them, no. So unlike exponentials, like if you throw a number in there, you can eventually find, raise it to that power, you can get that answer. Not always the case here. Okay? That's why it's a little bit more difficult. Okay? So one of the things that you need to be good at is going from logarithmic form to exponential form and exponential form to logarithmic form. There are 5 or 6 of each that we're going to translate, or we're going to go from exponential to logarithmic. I'm not going to do every one of these. We're just going to do a couple of these. So let's take a look at this right here. This is a true exponential equation. Each one of these is true, and it's very easy to see that it's true. 2 to the third equals 8. If I write that in logarithmic form, this is going to be log base 2 of what number? 8 equals 3. That's how we'd write it. Let's do this one right here. This is going to be log base. Okay, I'm skipping a little bit just in the interest of time. I don't think we need to do every one of these. Okay, this would be log base. Okay, need your eyes up here. Log base what? 9. Log base 9. Okay, if you're having any trouble, the 9's not hard to figure out. Where does the exponent go? Goes right here. Okay, and then the 3's got to go right there. So that would be log base 9 of 3 is 1/2. That's how we'd say that. Log base 9 of 3 is 1/2. Okay? Let's do this next one right here. Log base 16 of 1/2 equals -1/4. Now, that's a little bit difficult to see that that's the answer in either case. Okay? So this would be reciprocal of the 4th root of 16. So 1 over the 4th root of 16, that would be, what's the 4th root of 16? 2. So it is true. It's a lot easier to see here than it is to see here. And then these other two are kind of interesting. For this one right here, what would the base of this logarithm be? Log base e of x equals 2. Remember, the answer to the logarithm is an exponent. Okay? Now, we normally don't write it this way. We're going to talk about that, and you're probably familiar with how we normally write log base e. So we'll do that a little bit later. Let's take a look at this. Now,
Can you do the last one?
sure, okay?
Sorry, I don't understand.
So, log base, what would the base be?
10.
Got to be 10, because that's the base of the exponential. The answer to the logarithm has to be the exponent, so what goes here? A 5, and then this would just be a y.
So it doesn't matter what side it's on?
Nope, nope. Good? Okay, let's take a look at this next one. Please watch. We're going to do this one, and this one, at least to start off with. So this is a logarithmic expression. Again, it's maybe hard to see that that actually is a true equation. But if we write it in exponential form, it's easy to see that it's true. This is log base 6, so we're going to write exponential base 6. What's the exponent? 2. And what does it equal? 36. So if we read it in this form, everybody watch please. Log base 6 of 36 is 2 because 6 to the second equals 36. If we look at this one right here, 10 to the -3 equals 1 over 1,000. Exponential base 10 raised to the negative 3 equals 1/1000. Any questions there? Okay, what's the base of this exponential now? E to what power? Y equals 31. Now that doesn't make us feel any better because there's not really an answer. It's just changing from one form of the expression to a different form of the expression. Okay? So all you're asked to do here is just to change from exponential to logarithmic or logarithmic to exponential. Okay? Okay, just think for a second as to what this would be. Base 5, exponent x equals 12. Again, we don't really feel any warm fuzzies about that because it's still confusing. What is the x? Okay? But all we want to do on a problem like this is it will say change from exponential to logarithmic form and logarithmic form to exponential form. Any questions? Okay, so let's take a look at the next part. Okay, and please keep this in mind. This can be really helpful. Okay, if you're having trouble, if you're really good at going back and forth between exponential and logarithmic form, if you can't figure something out in exponential form, what could you do? Okay, change to logarithmic form. Okay, so if you can't figure it out in exponential form, change it to logarithmic form. Okay, and if you were to kind of enunciate everything, it is logarithmic. Okay, that kind of helps you spell it right. Okay, and if you can't figure it out in logarithmic form, what could you do? Change it to exponential form. So they're both really advantageous, just like sometimes it's better to work with a square root than squaring or something like that. Okay, which is the next idea. Okay, you're really familiar with square roots. But when you were first shown a radical, you probably looked at that and thought, my gosh, what is that? A weird division symbol or something? But then you get used to the fact that a square root is just asking a question. For instance, this one right here is just asking, what number do I square to get 25? And you get used to being able to answer that. It's going to be 5. Okay? Well, when you see a logarithm, you need to get used to the fact that it's just asking a question. So this one right here, log base 2 of 32. We want to simplify that. We want an answer to that. The question is, 2 to what power gives us this number right here? 2 to what power gives us 32? That's the question a logarithm is asking. And what's the answer on this one? Answer would be 5. Okay? So log base 2 of 32 is equal to 5. And again, you can think about why that's got to be true. Why is that the correct answer? Because 2 to the 5th is equal to 32. Okay? So do you see how converting back and forth from logarithmic to exponential can kind of help make sense of what these are? Very useful, both of them are. Okay? So let's take a look at these. And remember, all we're doing here is we're just asking a question. It's a new question, a little bit of a weird question, but it's just a question. Log base 2 of 8. 2 to what power equals 8? 3. Log base 2 of 32? That's the one we just did. Log base 10 of 10. 10 to what power equals, log base 10 of 100. 10 to what power equals 100? 2. Also 2. Now let's get a little bit interesting. We got to think about this. These look like nice numbers. They look harmless enough. 16 to what power gives me 4? It's got to be 1/2. Okay? 6 to what power gives me 1/6? -1. We doing okay? I'm seeing lots of shaking heads here, so that's good. Shaking in the right direction, that is. Okay, the next one, don't say anything out loud on this one. Log base 3 of 1/9 is asking us to figure out 3 to what power gives me 1/9. Well, it's a fraction like this one, so it's probably going to be negative. And 3 to what power gives me 9? -2. And again, if you weren't sure, just write it like this. 3 to the -2 equals 1/9. Does it work? It does. Again, exponential form for most people, because we're comfortable with that, is a lot easier to see. And how about this one right here? It is going to be 0. 17 to what power gives me 1? Any number to the 0 power will give us 1, so the answer there is 0. Okay, are there any questions? Okay, so let's come back to the starter question. You sure we're doing okay? All right, so let's come back to the starter question and let's figure out Well, if I have an exponential base 2, like I've got right here, let's figure out what the inverse of that is. So I would switch the x and y, so I've got x equals 2 to the y, and then I need to get that y down where I can work with it. Well, if you stop and think for just a second, there is no other tool we have in our mathematical tool bag that will allow us to move where an exponent is, other than a logarithm. And that's why they're so useful, is because we can move those same numbers around, those same expressions around. So I can take this, I could stare at this all day long if we hadn't gone through those ideas on that first page. This right here is an exponential expression. I want to get y by itself. The only way I'm going to be able to do that is if I write it in logarithmic form. So I'm going to write log base 2 of x is equal to y. And that's it. Now, I realize it ends up in the wrong order, so I'm just going to change it around. Y equals log base 2 of x. So, if this was the original function, if f of x was 2 to the x, then the inverse of that function is log base 2 of x. Those two are inverses of each other. Log base 2 and exponential base 2 are inverses of each other. So it says write the function and its inverse using function notation. I guess I should have written that down there. Okay. Then it says graph f and f inverse. So let's go ahead and graph these. Now I'm going to do the original one in red. That's just an exponential. So it's going to go through 0, 1, 1, 2, negative 1, 1/2, right? So it's going to look something like this. It's going to have a horizontal asymptote of y equals 0. And this point again, 1, 2, 0, 1, negative 1, 1/2. Okay, now, if these truly are inverses, and I'm going to do the inverse in blue, what happens from the function to the inverse function? What did I do? You switch it, right? You switch all the x stuff for y stuff. So every one of these points is going to switch. So this isn't going to be 1, 2, it's going to be 2, 1. This isn't going to be 0, 1, it's going to be 1, 0. This isn't going to be negative 1, 1/2, it's going to be 1/2, negative 1, it's going to look like that. And furthermore, it's not going to have a horizontal asymptote of y equals 0. What's it going to have now? A vertical asymptote of x equals 0. Okay? So the graph is going to look something like this. There is 1/2, negative 1. There is 1, 0. And there is 2, 1. Here is the inverse function. And here's the original function. This is 2 to the x. And this is log base 2 of x. Okay? Everybody with me there? Okay. You remember this from 1010? Good review though? Okay, so we'll make sure we keep this stuff straight. This should look familiar. Okay? Every function makes a shape. Exponentials make a shape. We dealt with those yesterday. We're pretty familiar with those. Logarithms make a shape also. So if we think about a general exponential, this is exponential base A, this is all the stuff we went over yesterday. Well, all we have to do is tweak this just a little bit, and we've got a parent graph for any general logarithmic function. So this is called log base A. You'll notice that it goes through the same points, we just switched their order. So it goes through, instead of writing down, everybody watch please, I want to make sure you've got this, negative 1, 0, and 1 for the x's. I write negative 1, 0, and 1 for the y's. This is always a 1. It always has an x-intercept of 1. And then this would be, again, that negative means reciprocal, right? So this is 1 over a, and that's a. The base still has to be a positive number other than 1. The domain. Let's figure out the domain now. If these truly are inverses, what should the domain be? Okay, should be what the range was for the exponential. So that's going to be 0 to infinity. And the range is going to be the old domain. So that's going to be negative infinity to infinity. And it has a what? Has a vertical asymptote of x equals 0 instead of horizontal asymptote of y equals 0. Okay? Any questions there? Make sense? Okay. Another quick example of some inverse functions. This is exponential base 4. We graphed this one the other day. It's going to go through 0, 1, 1, 4, negative 1, 1/4. So it's going to look like this, right? This is exponential base 4. That's the name. If I graph this one, what's its name? Log base 4. And what points does it go through? Okay, so it goes through 1, 0. The next most convenient point to graph would be 4, 1. And then this one is going to be 1/4, negative 1. So again, it's these points right here. You can quickly write them down. Negative 1, 0, and 1. That's a 1. Reciprocal of the base right here, same as the base right there. Those are the 3 key points it goes through. And again, we mentioned this yesterday. It's because that's where the bend happens. That's where the most curve happens. And then we've got this vertical asymptote of x equals 0. And we just want to label each one of those points. So 4, 1, 1, 0, 1/4, negative 1. Okay, any questions? Okay, as we've pointed out before, if we were to look at these, either one of these sets of graphs, they're reflections across the line y equals x. They're inverses of each other. So whether I've got exponential base 2 and log base 2, exponential base 4 and log base 4, those are inverses of each other. So this is huge. This gives us another way to do inverse operations. You know how to undo squaring, you take a square root. You know how to undo adding 3, you subtract 3. Those are inverse operations. So now we've got another set. Logs and exponentials of the same base are inverses of each other. They undo each other. Okay? So there are 2 exponentials and logarithms that come up more than any other. Okay? Exponential base e comes up a lot because it's the natural number e. It's amazing where that number crops up. Lots of formulas that we use, lots of places in nature. That's why we call it the natural number. And exponential base 10 comes up a lot because those are nice powers of 10. They're like the base of our number system. So their inverses or their logarithms are the 2 most commonly used logarithms. So this one is called the natural log. It's indicated like this, ln x, and that's actually how we say it. We just say ln x, and it means the natural log of x, and it's the inverse of exponential base e. Okay? If we just write log and x, we say that log x, you'll notice that there's no base here. Okay? It's kind of like when I write this symbol, I don't have to write that there's a 2 there for you to know that it's the square root. So this is log base 10. You just need to understand that. It's the inverse of exponential base 10. And there's no base on this one, but the n reminds us that it's the base of the natural number e. Okay? So this is ln x, log base e. This is log of x. That's the common log or log base 10. Okay? Any questions there? Okay. The cool thing about the 2 of those is they're the only 2 logarithms you're going to find on a calculator. Okay? So I can actually find really wild logarithms on a calculator. So grab your calculator real quick. If I want to find log of 5/4, make sure you type it in correctly. Here's the common log right there. 5 divided by 4 would be a good idea to close the parentheses there. And the answer is 0.0969. Okay, 0.0969. Now, you can actually check and make sure that that answer is correct because this is the answer to a logarithm. That's the answer to a logarithm. So what is it? It's an exponent. On what base? On base 10. So if I wrote this in exponential form, this says that 10 to the 0.0969 is 5/4. Well, let's double check that. On the calculator, I can check it by doing this. 10 raised to the 0.0969, 969 1, 0. Okay? Now, is this going to give me 5/4? It's going to be close. 5/4 is 1.25. It's close. Why isn't it exact? Yeah, because we rounded. Okay? Now, if I recalled that, and then I do 10 to that last answer, you've got the same capability on those small TI calculators, then it's going to be perfect, okay? Because it used all that decimal accuracy. It didn't round it or anything, okay? So, if we were going to type this one into the calculator, pretty easy. All we have to do is, let's grab the ln button. So ln of 15. Close the parentheses. Make sure you close the parentheses. Take that answer, divide by 3, hit enter. There it is. So 0.9026. And the last one, okay, we're going to type this in. We're going to get an answer. That would just be awful to do by hand. You really wouldn't be able to do it. You'd have to look it up in an old school logarithm table. Okay, that wouldn't be any fun. Think about how you type this in. Thank you very much. What am I going to start with? Very good. Start with a set of parentheses. The top has 2 terms. So we're going to do the ln of 100. Close the parentheses. There's that first expression. Plus the ln of 4. Whoops. ln of 4. Close the parentheses. Close them again. There's the entire top. Now, usually, I just get in this habit. We're going to divide by, I just start a set of parentheses. Let's put the bottom in parentheses. Okay? There would be the top divided by the bottom. That's the correct answer. Okay? Now, you can get away without that second set of parentheses on the bottom. You could just divide by log of 7, common log of 7. But that's the answer, 7.089. Okay? Any questions? Easy enough? Okay. So let's take a look at this next example. Again, because exponential base e and its inverse ln x is really important, let's make sure we know how to graph these. So this would go through 0, 1, 1 comma e, and negative 1, 1 over e. So here's that graph right here. Horizontal asymptote of y equals 0. Again, with an exponential, you can just write down those points really quickly. Again, exponential base e is the name of that. We've got the 3 points. What haven't we done on this, though? Domain and range. So the domain here is, what can you plug into an exponential? Anything, all reals. So from negative infinity to infinity. And what about the range? Got to be greater than 0. And does it include 0? It doesn't, because this is always a positive number. If I take a positive base, raise it to a power, it's always going to be positive. It can get really, really small out there on that negative end, but it never actually touches the x-axis. It never equals 0. Okay? Okay, and then we're going to do this one. This is ln x, or it's log base e. We could call it the natural log also. And it's going to go through these points. Same ones, just negative 1, 0, and 1 for the y's. 1 for an x-intercept. 1 over the base. Same as the base. So here are the numbers. This is going to be e comma 1. 1 comma 0. This one right here is 1 over e comma negative 1. That's the graph. We'll come back and draw the asymptote in just a second. Again, e comma 1, 1 comma 0, 1 over e comma negative 1, and here's our vertical asymptote of x equals 0. What's the only thing we haven't done on this? Domain and range. Now, domain and range, because we've already got the original function and we're graphing the inverse, should be pretty easy. What's the only thing I have to do with these guys? Just switch them. So the domain is going to be from 0 to infinity, and the range is going to be negative infinity to infinity. You could go back to those rules that you learned in 1010. Take this graph and squish it on the x-axis. None of this stuff is covered, so we start getting answers at 0 and go forward. If we want to know the range, squish it onto the y-axis, all the way from negative infinity to positive infinity. Okay? Any questions? Okay, so just like yesterday, now we're going to ease up just a tad. We're only going to graph 2 points in the asymptote. We'll label those and then state the domain and the range. Okay, so let's think about this for just a second. Every one of these, what is the parent graph for all 4 of these? If you had to name these functions, what's the name of these functions? Log base 2. Okay, so this is a logarithm. So we're looking for something that goes like this, has a vertical asymptote right there. So I'm going to graph the parent function right here. So it goes through these points. There's the parent function. That's the shape we're after. What does this do to the shape? Left 1 unit, right? So I'm going to take that shape, we know where each one of these is, and I'm going to move left 1, left 1, left 1. So we're right there. Now, before I start graphing this, I mentioned this the other day, do yourself a favor. Before I draw the shape, I could do one other thing that will make sure I get the shape right. What should I draw in first? Asymptote. Okay, draw in the asymptote. The asymptote is, what's the new asymptote? X equals -1. So by drawing that in there, here's what's going to happen. Okay, everybody watch, please. This is what a lot of people will do. If it's not there, they do this. I mean, they're just naturally in the habit of making a nice looking curve. This has quite a bend to it, and putting the asymptote in there helps you make that curve the right way. It bends around like this and approaches a vertical line. Okay? Label a couple points. Let's do these two because they're pretty easy. 0, 0. And what would this one be? If it was at 2, 1, and all we did is slide it back 1 unit, 1, 1. Okay? Domain and range. -1 to infinity. Okay, we backed it up 1 unit, so we can include those negative x's now. Okay, and the range, all reals from negative infinity to infinity. Okay. Same parent function. What does the +1 do here? Up 1. So I'm going to take this graph and move it up 1 unit. Now, does moving it up 1 unit change the vertical asymptote? Same vertical asymptote. So still going to be x equals 0. But if I move this point up 1, it would be there. If I move that point up 1, it would be there. If I move this point up, it would be right there. And again, I've got those 3 points. I can make the shape along with that asymptote look something like this. I would like you to label this one and this one. These two. Those 2 fat ones there. Jared, we'll give you the easy one. What's this one? 2, 2. Because it was at 2, 1. We moved it up 1. That's going to put it at 2, 2. Christopher, what's this one right here? 1/2, 0. Because it was at 1/2, -1. If I move it up 1, the x coordinate doesn't change at all. It's just the y coordinate that changes. Okay? Let's do the next one. The next one's pretty easy. McKay, what happened to log base 2 if we throw a negative in front of it?
That would be a vertical flip.
Yep.
Right? Yeah.
So that's going to be a vertical flip. So we're going to take this shape right here and flip it upside down. So instead of having a vertical asymptote down here, it's going to have a vertical asymptote up here. It's still going to go through 1, 0, right? But instead of being 2, 1, it's going to be 2, -1. Instead of being 1/2, -1, it's going to be 1/2, 1. And here's the shape right there. Okay? So, yeah.
On the test, if we just do the vertical asymptote on the whole thing, are you going to mark it wrong?
Like all the way up and down?
Yeah.
No, I won't mark it wrong. Okay, and who can tell me what happens here? Flips what way? Okay, because we're changing x, it flips it horizontally. So we don't have a shape that's like this. It just horizontally flips it. It's flipped the other way. So same vertical asymptote, but now it kind of opens up the other way. It goes like this. Okay? And again, you could label a couple of those points, right? We'll do the easy one, -2, 1 instead of 2, 1, because it just flips it around and goes the other way. Okay, any questions? Sure? Oh, thank you very much. Domain and range. Let's do that on this one. In fact, this one's kind of interesting on this one. What's the domain for this one? -infinity to 0, right? Domain is all real numbers. So this one's kind of weird. Remember, we said you can't take the log of a negative, and yet we're saying the domain is all the negative numbers. Why is that okay here?
Because if you plug in the negative number, there's already negative inside, so
Yeah, the very first thing you're going to do is make it positive, and then you can take the log of that number. Okay? Is that good? Sure? Okay. Now, so those are a little bit more advanced. You maybe did 1 or 2 of those in Math 1010. You also didn't do anything like example number 8 in 1010. Okay? So this one says, and you have a couple problems on your assignment like this. It says, find the domain of f and graph f. Determine the range and the asymptotes. Find f inverse, and then use f inverse to find the range of f, and then graph f inverse. Okay? Now, that's a lot of stuff to keep track of. Okay, now I want you to think for just a second. Okay, so everybody look up here. What is the base of this logarithm? Log base c. Okay, what's the inverse of log base c? Exponential base c. So when we find the inverse, we're going to have an exponential base c. Somewhere in there, there's going to be an exponential base e. Is that okay? Okay, so let's take a look at this. It says find the domain. Now notice it asks us to do that first. It might be easier to graph, but let's see if we can figure this out just by looking at this. Whatever we plug in here, remember logarithms are one of those functions that has domain issues. Whatever we plug in here, it better be, not negative or 0. It better be positive, okay? So x minus 3 had better be greater than 0. Which means x had better be greater than 3. In other words, the domain starts at 3 and just gets bigger from there. Is that all right? Okay, let's see if that matches up with what the graph would look like. What does subtracting 3 from x do to ln x? Moves it right 3. Right 3. So we're going to take that original parent graph, ln x, and we're going to move that 3 units to the right. So it normally goes through these points and looks something like this. We're going to move it 3 units to the right. So it's not going to go through 1, 0. It's going to go through 4, 0. So it's going to go through right here. It's also not going to have a vertical asymptote of x equals 0. What's it going to have? X equals 3. So here's the vertical asymptote, x equals 3. So that logarithm is going to look something like this. Now, did it tell us that we had to find the domain, or excuse me, did it tell us we had to label anything? Okay, so is that good? Is everybody okay with that? We've done a lot of labeling so far. Is that good? Does it look like the domain is from 3 to infinity? Yes, it does. Okay, what about the range? -infinity to infinity. Good there? Okay, now, I'm going to change colors because it said find the domain, graph it, find the range and the asymptote. So we've got all that stuff. And then it says find f inverse, and then it says find the range. Well, here's what we're going to do. I'm going to change colors. What's the domain and the range for the inverse? Just switch them. -infinity to infinity. 3 to infinity, right? Okay, now, let's go ahead and go through the process. This would be x equals ln of x minus 3. Oh, sorry, y, right? Switch to y. Okay. Is that better? Okay, stare at that for just a second. Do you know how to get y by itself? Can I distribute that through and say it's the ln of y minus the ln of 3? Nope, very few functions distribute, so please don't do that. So if I'm going to find the inverse, what form is this in right now? Logarithmic form. If it's in logarithmic form and we can't figure it out, write it in exponential form. So what's the base? E. What's the exponent? X. And what does it equal? Y minus 3. So if I get that by itself, it would be y equals e to the x plus 3. You with me there? Let's graph that. You know what exponential base e looks like. We practiced that yesterday. What happens to that graph when I add 3 to it? Up 3. So we're going to go up 1, 2, 3. Here's the horizontal asymptote, y equals 3. It's going to go through that point right there. And it's going to be growth. It's going to look something like that. If you tilt your head a tad, do they look like reflections across the line y equals x? You bet they do. Okay, they are inverses. By the way, just for the heck of it, what is this point? 0, 4. What's this point right here? 4, 0. Okay? And if we did get this right, if you plug in a 0, e to the 0 is 1, plus 4, or sorry, plus 3 is 4. Does that make sense? Okay. Any questions there? Okay. So we found the domain and the range. We found extra. They just said find the range. And we graphed the inverse. Okay? Let's take a look at this problem right here. And again, I'm going to do the same thing on this one. This one's slightly more difficult. Do you remember what multiplying by x by 2 does to the graph? Yeah, it's horizontal for sure. You'd think multiplying by 2 would stretch it. It shrinks it. Okay? And what does subtracting 3 do? Down 3. So if the original ln graph looks something like this, we're going to horizontally shrink it. So that's going to take this point that was right here, and it's going to move about halfway back. That's going to move about halfway back, and that's going to move halfway back. So this point right here is 1/2, 0 is what it would be. That's that point. Okay, now that's the right shape. Where do I need to move it? Down 3. So I'm going to take that one point. Now stop and think for a second. If I move it down 3, does that change the vertical asymptote? No. So I'm going to take this point, go down 1, 2, 3. That's the only point that I want to label. That point right there would be 1/2, it was 1/2, 0. What is it now? 1/2, -3. Okay? I can move this one down 3. It's going to look something like that. So here's what the logarithm looks like. There's our vertical asymptote of x equals 0. Domain. 0 to infinity. Okay, remember, domain, only the x's. Range. Yeah, it's still going to continue going up, so that's going to be all reals. Okay, I'm going to change colors again. I'm going to do this one in blue. Okay, so I want the domain and the range of the inverse function. Negative infinity to infinity, which makes sense because you can plug anything you want into an exponential. Range is going to be 0 to infinity. Okay, any questions there? Okay, let's go ahead and find the inverse. I'm going to erase this stuff so I've got a little bit of room to do the work. Switch the x and y. This is x equals ln of 2y minus 3. We want to get y by itself. Move the 3. x plus 3 ln of 2y. Stare at that all day long. The only tool you have to get that y away from the ln, away from the logarithm is, it's written in logarithmic form right now. We can write it in exponential form. So what would the base be? E to the what? X plus 3, very good, equals 2y. And last thing, divide by 2. So its inverse would be, I'm going to write it this way, 1/2 e to the x plus 3. Now, you know what exponential base e looks like. What does multiplying by 1/2 do, and what does adding 3 do? Careful. It's with the x. Left 3. And what does the 1/2 do? Vertical. Vertical changes do exactly what you'd think. So you'd think multiplying by 1/2 is going to shrink it. It's going to shrink it. Okay? It is confusing. You got to keep those straight. Vertical changes do exactly what you think. Horizontal changes do the opposite of what you think. So I'm going to take the exponential graph that used to look like this. So here's exponential base e. And I'm going to vertically shrink it. I'm going to make it half as tall as it was. Watch. I need you to follow this point. That point right there is 1. If I make it half as tall, what is it? It's a half. Then if I slide it 3 units, which way? To the left. That's going to put it right here. And my graph is going to look something like this. Notice that we don't change the horizontal asymptote at all. There's our y equals 0. And this point right here, its y coordinate is 1/2. What's its x coordinate? -3. And notice this. Look at this. If you can follow all of those transformations, finding the inverses, sliding those up and down, left, right, stretching, shrinking, all that sort of stuff, isn't that pretty cool that the same point with the x and y coordinates switched appears on the function and its inverse? Okay? And did we get the domain and range right? We did. Okay? Any questions there? Okay, I think you have 3 problems that are like that. Okay? I'm going to end with this. I think this is enough that you could do the homework. Tomorrow I am going to come back. We'll look at these problems. We'll take a few questions. We'll correct everything then, but I do want you to watch this and fill in these blanks. Logarithms are just another way to write exponential expressions. We'll just say exponentials. The answer to a logarithm is an exponent. If you're having trouble in exponential form, write it in log form. And if you're having trouble in logarithmic form, write it in exponential form. If you remember those 4 things about logarithms, there really isn't anything you can't figure out if you put your mind to it. That includes the last page there. So I bet you could figure all of those out. Okay? No, our goal should be that at the end of class tomorrow, you won't have any homework. Okay, so get started on 6-4. If you run across something like this, don't worry about it. We'll have some time tomorrow. I'll do those problems to start with, and then we'll just take questions and give you time to work. Remember, there's a quiz on Monday.